So, okay. So just recall that the problem that we are interested in will still be vertex cover. Okay. So again, and we are still talking about decision version. G, K, question, does G has a vertex cover of size at most K? And towards the end of our lecture, we already saw an algorithm with running time. Okay. So for the brevity or for the clarity, I will just not worry about this term. Okay. I will only, for now, anyway those polynomial factors, just to give emphasis of what we are talking about, I will not worry about this. And some of you did something and say, hey, I could also write like this. Okay. So this is basically, this algorithm is like upper bounded by this. Okay. Now my question to you is that, okay, what better? And if you have seen FPT and this and that, then don't say like what better? What kind of algorithms can I say? Yeah, this is an algorithm in this regime or this. Now, why this algorithm is interesting in the sense that notice that if I was asking you that does, say for example, k equal to 10, right? Then this algorithm is still polynomial time, right? So in that sense, it is an algorithm which is sensitive to what size vertex cover you are trying to select or pick. But that's not what I wanted to say. Given that this is an algorithm, what will you consider an improvement over this? Okay, what running time could we say is better than is the question clear? Like what running time can I say? This is why I say let's, for now, let's not worry about plus 1. Suppose this is just n to the power k. What form of the running time will I say? It's an improvement over n to the power k. Is this an improvement over this algorithm? No, yes? Yes or no? Okay. I'm going to try to, so for example, this algorithm, we try to enumerate all subsets of size k, and that is how we got n to the power k, right? Now I'm trying to ask you an algorithm which is like, maybe you don't need to enumerate all subsets of size k, maybe k minus 1 is enough, for example. Is it always possible? You get my point, right? Or, so algorithm of the form n to the power k minus big O of 1. Like this is also a form of algorithm. Okay. Another kind of algorithm we could try, okay, maybe not this, n to the power little o of k is possible. This is definitely an improvement, because what is little o of k? Can you tell me a couple of running times which I can say, hey, it is n to the power little o of k? Can you tell me one running time when I say n to the power little of k? Can you think of an one? Huh? Very good. So for example, if I had n to the power big O of root k, it is an algorithm of the nature n to the power little o of k. Right? So basically, I'm going to replace here a function which is little o of k. That's all that we have to do. So this is also n to the power little of k, right? So there could be various form of running time that we could expect of this nature, of this nature. What else form of running time we could think of? Which you should be able to say, this is better than this. And better than is not all values, like there is some function of n after that. If you I mean, the way we talk about in terms of asymptotics, it's not that for each value of no, I'm not talking in that sense. What other algorithm we can say, hey, if I can design an algorithm whose running time looks like this, then it could very well be better than this. Like, why are we designing an algorithm of any kind? Is because we want to design an algorithm which is better, good. No. No, like certain values of k, like it's okay, but like we can say, hey, if I say k is like your variable, n is like your variable, right? So we say, look, for example, now say fixed k, for now fixed k example, what number seems to be better than n to the power k? Okay, if I write n to the power 100, okay, what number do you think you can write better than n to the power 100? Which is not of this nature, because this nature I can write n to the power root 100 and this and that. Okay. What? 2 to the power 100, right? Is definitely better than n to the power 100. Okay. So basically, now 2 power k is definitely better than n to the power k for any n greater than or equal to 2, irrespective of k. Irrespective of k, right? Whatever may be the k. But if I say this is less than or equal to n to the power k for all n greater than or equal to 2. This is correct, right? Okay. Similarly, but look, this is exactly what I mean. Like, if I take slightly bigger than a constant size graph or instance, I'm always good. Okay. But what about this? Is this better than n to the power k? No? N greater than? Why? Yeah, it's 2 power k, right? It's not 2 power, it's this. I claim that I can you say something like this? For all n greater than equal to some 10 to the power 10 or something, can I ever say this? Or what will I say that this is greater than this? Like, I want to say this number, for all this function is better than this. Can I say this? You understand my question? 2 power k was very easy to this. Okay. What about this? Let's see if you can at least, can I say this? It's just a function, right? There's a function which is 2 power k square, there's a function which is n to the power k. And I'm claiming all the time that this is better than this. I take logarithm, okay? K square is in the left, should be less than equal to k into log n. Excellent. So all I care that n has to be greater than, so for all n greater than equal to 2 power k, this holds. Right? So right? Okay. Here what can I say? 2 power k. I want to say this is less than n to the power k. So let's take one log. So 2 power k should be less than equal to k times, right? Okay. Take another log, no? So k should be less than equal to, let's say this, log n to the power k. That's it. So what will I get from here? Okay, or rather, suppose this is k log n. Okay, so now 2 power k should be less than equal to k log n, or rather 2 power k by k should be less than equal to log n. Right? Now take log again. Okay. Now if I take log again, or rather from here, n has to be greater than 2 power. That's it. So for any k, there is some n which, if you go larger, and then this happens. Right? So what did we prove? So for every k, what is that called? So what did we manage to show from here? Let's try to understand. Okay. So you fix some number k, whatever that is, right, and you write some function. Okay. And now you take n. Okay. In the beginning, and now I want, so now I vary n. Okay. If n is small, then this number is smaller. But actually there exists the moment n becomes greater than some function of k, there always you will be able to find some function of k. So the moment n becomes more than that, this becomes smaller than this. And this is okay because now you have fixed k, right? In certain sense you have fixed k, and what are you varying? You are varying n, right? So ultimately this has to overpower this or go beyond this quantity. You understand my point? So now, in fact, this is not true about only these functions. This is true about any function which only depends on k will be smaller than a function like n to the power k, where n is allowed to grow. Okay? You understand my point? Okay. Okay. So look at. So the way to look at this problem is, okay, I fix k and I vary g. I fix k and I vary g. You understand my point? Because what did you make an algorithm for? You made an algorithm for, if you notice, we said, hey, look at this n to the power k algorithm. Oh, this is polynomial time when I fix k equal to 50. Right? K equal to 50, this algorithm takes times, say k equal to 50. Right? This is n to the power 50, independent of what your instance size is. Okay. But what this tells us, okay, so now let's fix k equal to 50. Right? Now, and suppose I had another algorithm which is like 2 power k times n square, or for now no n square. This is what my running time is. Now look at this, k is 50. So in the beginning, 2 power 50, this is what we are trying to beat. This is what we are trying to beat. right? And what is allowed? Size of the graph is my variable, which is going to change. If the size of the graph itself is more than this, definitely that choose 50 is going to be more than this quantity. You understand my point, right? So this is the right way of viewpoint, right? That once I fix k, and what am I varying? I am varying my graph. As the sizes and sizes and sizes and sizes will increase, any function of k, any function, because all you have to do is take n, which is more than function of k, right? So in fact, for any n which is your function of k, this is always going to be better than n to the power k, right? So this is the right viewpoint on this, right? So why did I make a better algorithm when I compute this compared to n to the power k? Because hey, pick up any k, eventually n to the power that quantity is going to take over this quantity. Okay? Okay. So this is the, I mean, like, so this is a kind of better, there are several viewpoints and you can like whatever viewpoint, but we have just done a basic algorithm course, and what is our viewpoint? Here's an algorithm for which I can design polynomial time algorithm, and the question is, can we do better, 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 and what is the threshold we can stop? Now for these NP hard problems also we can make some form of algorithm, okay, and now we can always ask questions, what is a better in that sense, what is an improvement over that, and the forms of algorithm, the kind of algorithms that you design form a complexity theory, form an algorithmic theory for these kinds of problems, okay. And in this course we just want to study the algorithmic complexity of these kind of problems, or basically vertex cover problem, okay. Okay. So what will we do for some problem? So now, okay, so basically what are we trying to say? So we say, look, so let's, okay, so given this, what is our best form of algorithm? The best form of algorithm is, which is like this, okay. Now let's give them some names, okay. Okay, these are, so why n to the power k minus 1, right? We could allow any n to the power g of k, any. Why? Well, maybe for vertex cover it was k, but maybe in other settings maybe k square is better, maybe n to the power 2 power k is better, or that is what we are able to achieve, right? So maybe this is a good running time, but maybe for some problem this is a good running time, okay. I will tell you, for many problems you can't even construct this. Give me 2 minutes, okay, and they all are NP hard problems, okay. So just give me 2 minutes and I will give you an example where even designing this seems very difficult, okay. So we'll get there, okay. So these are the kind of algorithms, we'll give it some name, okay. So that name is called FPT, okay, whatever that means. You can, if you wanted, you can give your name, and that's perfectly fine. All you care about is that you are trying to make an algorithm whose running time is this, whatever name it is, okay. Or you are trying to design such kind of algorithm which is called XP, okay. There is a meaning, but it doesn't matter, you write some name, okay. But now we have made a class, such algorithm and such algorithm, and we always know such algorithm is always better than these kind of algorithms. For the same problem, this running time is always worse than the running time of any of this nature. Then what is the question? So like, what is my goal? I mean, polynomial time algorithm is always better than quasi-polynomial time algorithm, right? Polynomial time algorithm is always better than something bigger. But then what is the big question? Can we really design a polynomial time algorithm? You get my point? So, given a problem, what is the question we see? Does it admit an FPT algorithm? That's the first question. First question, right? If not, how do we show this? How do we prove this? So this is like a flow chart of research, right? So given a problem, I ask this basic question. First, I try to do this. Maybe I will succeed, then hey, I'm happy. I don't care about anything else. But maybe I do not succeed. Then I want to have a certificate which says that such algorithms do not exist. Right? This problem cannot have an algorithm of this form. Okay? And or does it has an XP algorithm? Okay. So I could ask various questions, right? Okay. Now you might ask, but like, hey, all the problems I can think of, this seems to. Okay. So let's see some fun. You know that vertex cover on cubic graph is NP-hard? Vertex cover, even if I give you a graph with maximum degree bounded by 3, it's NP-hard. You get my point? Okay. So vertex cover on cubic graph is NP-hard. It's known. And like this, like, okay, check, or take your reductions, do some subdivisions, try to make it, it should work out. Okay. Now I said, okay, fine. Okay. So my input is G, K. Question remains the same. Does G has a vertex cover of size at most K? But I said, yeah. Now I do not. I want an algorithm which is f of degree times n to the power big O of 1. Do you think we can design such an algorithm? Look, it's just about, it's about designing an algorithm and bounding the running time by some function, right? So I want to design an algorithm where I want to bound the running time by this function. You understand my point, right? Problem remains the same. It's just that, and the form of the running time I told you. But now, in what function do I want to bound the running time? It's up to me. I mean, I could bound in any function I desire. Some may be meaningful, some may be meaningless, some completely useless. Okay? But now, I want to measure the running time of this algorithm. I want to design an algorithm for vertex cover, but the running time of this algorithm, I want to bound as a function of max degree, not even anything. Max degree times n to the power big O of 1. And now my question is, hey, looking at the board, do you really think we can come up with an algorithm whose running time can be bounded as function of max degree times polynomial? Is the question clear at least? Right? So we are in the world where all we care about that we want to design an algorithm. That's it. Right? Rest is a jazz. Different field produces different jazz, different notations, different symptoms, because they all try to measure something different. Someone tries to run polynomial time, someone wants to run indifferent time, someone wants to care about some other kind of resources, someone wants to care, oh no, extra space that I will give you is only this, someone says, oh, input is coming like this. I mean, you can design anything in your life, but at the end of the day, there are some, it's like a chess. I have given you some rules, you can only play your moves based on those rules, right? So rules are clear, you have to design an algorithm, that's all that I care. But I will tell you in what function do I want to bound the algorithm. Now, given that I told you, I want to bound the running time of this algorithm in this form, okay? You have to start thinking along those lines. Right? So think about you're trying to write a program, and based on what resources I'm able to provide you, you have to design an algorithm which takes care of those specifications, right? So here's my specification. I want you to design me an algorithm for the vertex cover problem where the running time I want to upper bound is f of max degree times polynomial, right? So this is my question. You can come back and tell me, hey, unless bad things happens in the world, you should not be able to do it, okay? Can you say, what could happen if you design such an algorithm? Right? What happens? So I can prove my first inapproximability result or hard intractable. Unless p not equal to np, no such algorithms exist. Is this correct? What is the meaning of this? If you give me such an algorithm, I am going to solve an NP complete problem in polytime. So if I give you this algorithm, which NP complete problem will you solve in polynomial time? Do you understand the question, right? What is the meaning of this statement? Basically means if I give you such a black box, if I give you such an algorithm, which NP complete problem can you solve? Right? So can I solve this problem in polytime? Because what is the max degree of a cubic graph? 3. So what is this? F of 3 times n to the power big O of 1 is what? Is it not polynomial time? Because not possible, no? Okay, great. So what did I say? Yeah, we said that we would like to design such an algorithm, we couldn't do it. So we should try to design last algorithm, like at least one more thing. Okay. Okay. Okay, so now what I want to bound n to the power, just so that you don't confuse, some other function of max degree. Do you think such an algorithm can exist? I want to say the same thing. Unless p not equal to np, unless p not equal to np, such algorithm. Okay, you're right. Sorry, my bad. Does that make sense? Right? Because n to the power, it's really a fixed constant which only depends on 3. So no such algorithms exist, right? So for the vertex cover, right, while when I asked you to measure the running time as a function of the solution you are trying to construct, okay? So look at the two things, right? We made an algorithm. Now look at the vertex cover, right? We did make an algorithm which was running time n to the power k plus big of 1, right? Yes, happy face. Okay, but here we say no n to the power f of max degree algorithm. You agree? That's what we showed. So now what the problem is same, okay, but I'm saying to you that okay, if you want to measure the running time of your algorithm as a function of k, which is solution size, okay, what is this k? Is size of the solution we are seeking. What is here? It's a maximum degree of the input. Right? So we are saying very many things. We are saying, look, just imagine for a moment, like of course it's forward, but just think what we showed. We said, look, I mean, you cannot design any algorithm which can depend on any crazy function of max degree for vertex cover. You get my point? So like same problem, it could turn out that if you try to design an algorithm whose running time you can bound as a function of something, it may not happen. But if you try to bound the running time as a function of something else, it may happen. Right? So the problem remains the same. Now, but there is one very important parameter, right? What about, we also made an algorithm yesterday whose running time was what? That's the first algorithm that we designed. I claim to you this is of this form. For what value? For what? I am claiming that this algorithm is of this nature. But what is the object which I am trying to use to measure the running time? What? Get my point? No. I am saying, I want to say this algorithm is of the form, this algorithm is of the form f of something times n to the power big O of 1. What that something can I say? Excellent. Okay. Right? So I have shown to you 3 algorithms. Okay? 3 algorithms. But now among them, I can start comparing things in life. Okay? That's what I mean by comparing things. Okay? But do you understand? For the same problem, okay, I did design you an algorithm which is excellent. Okay? I did design you an algorithm which is semi-excellent. Okay? And I showed you that you cannot design any algorithm which is of this nature. Okay? Okay. So now let's try to do some anatomy for these things. Okay? So let's keep that here. Okay? Okay. Size of the solution we are seeking, this is k, and n is the number of vertices. Is there any relation between them, or they are uncomparable?
Always less than n.
Excellent. Right? So what does it mean? So if there are 2 structure or 2 numbers, let's say alpha and beta, 2 numbers where alpha is less than or equal to beta, and if I design an algorithm with running time f of alpha times n to the power big O 1, does it imply also that we have designed an algorithm with running time f of beta to the power n to the power big O of 1? This also implies that we have an algorithm with running time. Do you agree? Right? So here, existence is like a taxonomy, you know. So existence of f alpha, so existence of fpt in alpha implies fpt in beta. Okay. And if I showed no algorithm running in time f beta to the power n to the power big O of 1, what does it imply?
No alpha, f of alpha. There will be no f of alpha.
What is opposite?
F of beta, if we have an algorithm with f of beta, then it implies alpha.
Think for a minute, no? You just made a 2 power n algorithm. Does that imply that you have a f of solution size poly n algorithm? What will this imply though? There is no algorithm that I can bound with a bigger number. How do I expect to design or an algorithm or bound an algorithm with a number which is even smaller? You get my point? I mean, just common sense. If you apply common sense, like those reductions and this are just common sense. It's just that we do not spend enough time thinking about them. Okay? So no algorithm running in time f alpha to the power n to the power big O. So you can create a taxonomy of numbers, structures, objects with which you want to measure the running time. So now that we can do many things for a problem, what people started to do is that, okay, fine, let me tell you as a part of the task itself that I wanted to design an algorithm where running time should be bounded as a function of this object, this quantity, right? So as a part of input itself, I'm going to ask you, right? Because I could design many things, I don't know what you want, right? So you have to specify me in which form you want me to design an algorithm to bound the running time, okay? So this is where the word parameter comes, okay? Okay. So not only this, I have to also tell you, right? So what are the parameters did you see?
Solution size.
No, that's not the first thing we saw.
Oh, first is vertex size.
Number of vertices. That was one. I could also ask you size of solution. I could also ask you max degree. I could also ask anything else, whichever you feel. I mean, so now what function do you want to measure is just a question about how meaningful or not meaningful the question becomes, right? That's one thing. Now let's add more questions to our science knowledge, okay? So okay, we can do this, great, happy. Now that we've showed these two things, so suppose this is an alpha and this is a beta and this is like this, okay? And I know there is an algorithm with running time f of alpha times n to the power exist. What should be the next question should I be asking? Of course, there's one question that there are few questions that we can ask. How small function of alpha? That's one thing. But like, let's not at this point of time. Let's not worry about optimizing this f. That's a very natural question. We'll get to that. But I'm asking more taxonomically. What should be the next big idea if I wish to say, okay, fine. What should I find like that so that I can say my new algorithm is definitely better in some sense compared to this algorithm. You get my point? I design an algorithm, but I say, hey, so for example, if I found some number delta which is even less than alpha and for which we can design such an algorithm, then in some sense we have designed, like it's about running time of the algorithm for a problem and we want to bound. So we have found a quantity which is even smaller than what existed by which we can bound the running time, right? So this is about trying to find what is, like, so if I showed something is fpt with respect to this parameter, what is the other smaller parameter that we could show the same kind of result? So this is asymptotically behavior, like this is doing better. And now, so this is one flavor of question, right? And if I shown that it is hard with beta, what should I do?
Then next, which number for which?
No f of beta n to the power big of 1 algorithm. Then what should I try to do?
Some number greater than beta, something greater than beta.
Okay.
If we can
Say
have a-
theta. And you can show no g theta n to the power big of 1 algorithm. So when I am designing an algorithm, I should push leftwards. If I am designing in hardness reduction, I should push forward. Okay, this is just a simple text. Now you understand, right? Like in the world of polynomial time, there's just one object that I could push, which is it's a unidimensional, right? Because what is unidimensional? It's an input size which we try to design an algorithm which with respect to input size goes this side or goes that side. But now I have two things to play. I have two things to play, input size and something. But for now, if I forget about input size, then there's a parameter which, what can I find? Another one can I find? So it is a world of this. Okay. And now you can ask which delta, alpha, beta, theta should I choose? That is something which you get from experience and the kind of question people are asking in the literature. You will feel, it's just that I cannot tell you this is better, that is better. Okay. It is, yeah, but one should always strive to, I mean, because of this flexibility one can define many kind of parameters which may be very repetitive, or it could follow from the known results because of, like, if I do show some combinatorial relation between them, whatever, right. So one needs to be very careful what parameters to choose, right, in order to bound the running time of the algorithm. Okay. 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 We will see, we will add more questions to our studies as we go forward, but for now we will stick to these designing these kind of algorithms for now. So for example, in my graph theory lecture I said, right, this plus 5, it's a different parameterization, right. Right. I am saying, look, I know that every graph anyway has a path of size diameter, but can you give me slightly more? So diameter is not my parameter. That extra beyond diameter what I am asking is my parameter, right. So like you change your questions, you make your life difficult so that you get to do nice combinatorics, nice structure theory. Okay. I mean, you have to be very clear what is your objective. Okay. If your objective is to look for better combinatorics, better structure theory, then you have to ask more and more intuitive, inbuilt structures. Okay. Okay, fine. So that was about moral of the story. Okay, so let's. Okay, so okay. So now I look. Many of you have seen several algorithms of vertex cover. It is not. It is not meant for what knowledge you have. It is meant for people who have absolutely not seen this before. So even if you know, keep it to yourself. Okay. And those who have seen, maybe I can give some difficult task, but like, so for example, those who knows this jargon, try to design an algorithm for vertex cover using color coding. You are not allowed to use anything else. Okay. Let's see if you succeed. Okay. Okay. So let me. Don't worry about these jargons. These are like, don't worry. Like, we will see. Okay. So now what I want to do. Okay. So I want to design an algorithm. Okay. For vertex cover. So up until now we saw an algorithm with running time n to the power k plus big over 1. So either I tell you that there is no such algorithm, or I try to design such an algorithm, right? So let's put an emphasis or effort on trying to design such an algorithm. That's my goal. How will you go about designing an algorithm? For vertex cover, according to you, which vertex do you think is an important vertex? Why? That's not even good for approximation, but it's a good point. See, it's a good point. Does it make sense? Now, what is our goal? I have a graph, right? And I want to find k vertices such that every edge is covered. So the first thing which one should do is to draw such graph. So if I draw such graph, so how should I draw? I write on the top, this is my vertex cover, and which I call it S. What is remaining? What's the property of the remaining object? I know they are independent set, but it is not for you or you. You have a question, right? I gave a question to all of you people. Those who know, have a question now. I just not told a question, uttered a question, no? No, you didn't hear? Yeah, so think about that. So, what is this? Excellent. So this is the first thing which you should do. For any problem of this nature, draw this graph. Okay. 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 So now if I told you, if I gave you this independent set, can you then you know the vertex cover? If I told you this is your independent set vertex, can you tell me the vertex cover? Excellent. See? Okay. So what you're telling me is very funky, is that here is my, let's call this I independent set. Okay. If I gave you this independent set of size n minus k, okay. If I gave you an independent set of size n minus k or greater than, if I gave you this, then you know, you just take its complement and this. Okay. Now I'm asking you, but n minus k is too much, you are asking far too much. If I ask you, I may not be able to give you all n minus k, but I still can give you some subset which is an independent set. Will that be enough? I am saying to you that I cannot give you this, too much, you are asking far too much from me. Like, I don't have, okay. But I can tell you that, hey, I can give you some vertices which say W, whose size is, we'll worry about it. What is the smallest size W that you think if you can get from this I, you can get S? You understand my question? I told you that, oh, if I gave you I, you knew what S says. But I am not willing to give you whole of I. I can only give you some small subset. So now our question is, what is the smallest subset that probably we could get from this I that will help us construct S? So like if I know this, I say, hey, oh, if I know this, then I say, hey, look at these objects, this is your S. Okay. Up question, now it's for everybody. Let's say, is my question clear? Okay. So when I gave you I, you could reconstruct S. And what is the procedure you told me to reconstruct S? Take complement. Excellent. I didn't say anything. This is perfectly. I said, but I cannot give you this. Now I'm asking, what is the smallest subset W of I? What is the smallest subset W of I? If we had, then we could reconstruct S. So I want to construct this, and I have told very W is a subset of I. It is important for a minute. Otherwise, we will be in trouble. Okay. I was disjoint from S. No, that is why you can say take complement. So I want it to be disjoint, but not very big size. Oh, there is no isolated vertex. So I is equal to n of S.
One idea is this subset take the complement, it will create a vertex cover of itself. Now remaining edges which are not covered, consider it a separate graph, and brute force will give 2 to the power that remaining.
Oh, we are going too far away. I have a very specific question.
So this 2 to the power something should be less than, like it preserve.
No, my answer is Pauli. In fact, linear in K, if that helps. Okay. I mean, if you tell me this, I will be happy. I can prove, we can prove even smaller, but like, let's not go there. It's easy. Think for a minute. What? No, W is a subset of I. So we have this S which is fixed, there is an I, and my W is just subset of this I. Okay, so let me.
So we want to find the vertex over size k.
No, I want to get S.
S has size.
Size at most k. Okay, and let's assume that S is minimal. You know what is minimal vertex cover? Minimal vertex cover of size at most k. What is minimal? No S prime subset of proper subset of S is a vertex cover. Okay, this is the meaning of it. Like if I take any element out, that doesn't remain a vertex cover. So that's a property. So that is what it is, and that is of course size at most k. What W can I get?
So we take the in the complement graph we take the common neighborhood of W.
W.
Like
W is what we have to know.
we are given.
What is the smallest subset W of I? If we had,
Yes.
then we could construct S.
So we have W.
No, we don't have. We have to construct that W.
Okay.
What is the W that we could come up with that I say, hey, if you gave me this W, then I know how to get S. So for example, in the beginning he said, take whole of I. That's a good W, because once I gave you this I, his algorithm was take its complement, and you were done. I said, but I has size very big. Okay, can you do something smaller? And still say something of this nature, maybe not complement, maybe something else. Yes. That's whole of I. There are no isolated vertex. That's whole of I. Every vertex in W is adjacent to YD. Okay. Okay. That's a good start. So what Ananya is saying to me is that let's construct a W with the following property, that here's a W. Okay, so W will consist of, so he says let's pick up a vertex here which has unique neighbor in S. That's what you said, right? If there are too many vertices with that property, then what can I do? Look, what you said, first of all, there are several things. Okay, pick all vertices W in I such that W has a unique neighbor in S. Am I right? This is what you said? It's a good start. But what's the problem with this? Size could still be very large because there could be lots of people. For him, there's a single guy. But why did you want to do this? Like, what is your motivation? Then we will see if that motivation is achieved. First of all, there are two questions. Okay? Why such W exist? Right? That's a good point. No? Why such W? There may be no W with unique. Everybody sees several people. It could happen, no? Okay. Why such W exists? Let's say they exist. Now prove to me why they exist. Such W exist. Excellent. Okay. What is he says? For every vertex in S, there is some edges or some vertices which are only adjacent to him. Why? Because every vertex, every edge which he covered is also covered by someone else, then this is not a minimal vertex cover. Okay? So what is your answer? Since S is a minimal vertex cover, for every U in S, there exists a mate, say W, okay? For every Ui in S, there exists a mate Wi such that Wi sees only Ui in S. And this is true about every vertex in this. Okay? So basically, now we should draw more pictures. Okay? There could be many mates, no? You are promised that there is at least one mate, but there could be many mates. Okay? So we'll get there. Okay? So at least now I can take my I and try to here is U1, U2, say UK, mates of U1, mates of U2, mates of U3, mates of UK, nobody's mate, right? So who are these vertices? Who has at least 2 neighbors in UI, right? So these are your mates, okay? So, but I know for sure, because S is minimal implies, let's call this set W1, W2, W3, Wk, implies for all I, Wi is non-empty. Do you agree? I'm doing structure theory, right? So because whatever C says, look at W1, all the vertices which are mate to U1. What is W2? All the vertices that are mate to U2, so on and so forth. And because of this argument, I know each of Wi's are non-empty. Okay. Now, Ananya, what do you want to say? What happened? How can I construct W from here?
Choose one from each of these.
Okay. So everybody says, okay. So here's the construction for W. Okay. So now we construct W. So everybody tells me, okay, construct W, where Wi is element of capital Wi, one each. If I had this W, can you get S? What is S? If I gave you this W, can you construct S? Huh? What is S? Okay. What is S then? What? Neighbor of? No. Is this correct? S is equal to n of W. Please check. Pick up a vertex. Where are his neighbors? In S only, right? He does not have any neighbor here because this is an independent set. It's important point. Is that fine? Okay. In fact, now if I knew this W, look at any W tilde which is contained inside W and contained inside I. If I gave you this property, then what happens? Can I say the same thing? I claim to you for all W tilde which contains W and contained inside A, S equal to, because where are these guys neighbors? Here only, no, because it's an independent set. So I'm using the property independent set. Okay, excellent. How do we use this to design an algorithm?
So what is this nobody's name?
Like these guys has at least 2 neighbors here. Is that correct? Or rather, I think this is not the right way to say. Okay. So I think I'm not saying something right. So it's not that when I say mate, there is an edge which only he can cover, nobody else can cover. You understand my point?
Yeah, because
WI can see only UI. It should be only WI can see UI.
Only?
When we define the WI,
What do we define WI?
we don't WI can see only UI. We should write only WI can see.
Only UI can see?
Only WI can see UI.
if I see at least 2 vertices, then it should be sum of the
Wait. What are we trying? No.
Here the W is a disjoint term.
Notice okay, so this okay, so what did I say? Okay, so let's write. Okay, what is my Wi? Okay, let's say nothing more. Let me see. Wi, what is my Wi? Is they are not pendant. This is not correct. So let's write what is Wi. Wi is those W, okay, such that W sees U I. That's it. This is what my definition is. W sees UI. There is some edge which is inside. That's all that I care. Okay. Think about this, no? Think about this, okay? What you want? For every vertex here, I want to pick one neighbor each. That's all that I care. Because if I pick, for every one I picked a neighbor. For U2 I picked, maybe it's the same neighbor, I don't care. But if I knew that subset of vertices, and if I told you this, what is its neighborhood? It's going to be S only, because here it has no neighbor. You get my point? It's much simpler in the sense that I just try to follow the chain of Ananya, but it's much simpler. Much simpler is if I told you some x such that for every vertex there is a neighbor in X. So so if I gave you X, why n of X is not S? For every vertex if I find a neighbor, so imagine that I gave you a set W, okay? I want to say n of W is equal to S. What do I ask for W? That's all that I care. What do I ask from n of W? Where W is subset of I, and all I care about is that n of W is equal to S. So what should this W contain? W is a subset of I, and n of every vertex in UI should have a neighbor here. That's all that I require, right? And so because it's a minimal solution, everybody must be covering some edge, right? Which implies that Wi's are non-empty. That's all that I care. Minimality just guarantee wise that like there is some like it's not that this is a vacuum, right? This W must be covering some edge, otherwise you would have moved it down, no? So if it is covering some edge, it has some neighbors here, no? Pick that neighbor. So W just consists of a neighbor each of these guys. If they collide, I don't care, right? But I needed to guarantee that for every UI, there is some guy who is below, and that is guaranteed by the fact that S is a minimal vertex cover. That's all that I'm saying. Yes? I am picking one neighbor. Just pick a neighbor each of U1 to UK. If you pick one neighbor of each, now write open neighborhood of that set. Where are its neighbor? Not here, they are here, right? But for everybody there is one guy here, then he must be seeing him there, no? That's all that I wanted to say. W is of size at most K. That's all that I care. I did not say this. So my W is basically okay, maybe I should have. So so basically, if you want a very simple thing, what is W consist of? Like, pick a neighbor for each Vi that is contained in I. That's all that I want to say. This is all that I want to say. Okay? And why such W exists? Because my S is a minimal vertex cover, which means for every vertex in S, there is some edge that it covers. If it covers some edge, means it has some neighbor which is in I, right? Because if all his neighbors are in S itself, then this vertex is useless, right? I could have moved it down, right? You understand my point? Imagine that you had some vertex S which was adjacent only to a vertex in S, and it has no neighbor in I. Then if you move him down, it is still a vertex cover. So it's not a minimal vertex cover. Okay, that's all that I'm saying. Okay. Now, this is still true. If I give you any W tilde, which is subset of W, and contain inside I, S is equal to n of W tilde. Do you agree? Because where are the neighbors of W tilde? That is exactly equal to S. That is contained inside S, and because it contains W, it is equal to S. So, can you think of an algorithm now? Okay. Okay. All good? Okay. Okay. So now I want a process. What I want? I want a process from you. Okay. What I want to process? A polynomial time process okay, whatever, such that it constructs partition V1, partition V2. What it does? Construct partition V1 and V2. And what is the property? Let us see. First property, S is contained inside V1. Second property, W is contained inside V2. That's all that I want. So if I prove this, then W is contained inside V2 means where it is contained?
In I.
And this is contained inside I. Right? Because it does not, if V2 doesn't contain S, then S is fully contained inside I. Can I construct this? Okay, let's say any process you can think of. What happens if we do a random partition? Let's do a random partition. What is a random partition? Okay, so here's my random partition. For every vertex, I toss a coin. Okay, what is my process? For every vertex, toss a coin independently. Okay, independently. Okay, if head, put him in, else put in V2. That's my process. End of it. That's it. It's a polytime process, right? So this way I said polytime. Now I want to compute what is the probability of happening this. Have you seen randomized algorithms? Okay, even if you have not seen, like, there's nothing. It's just I gave you a process. I'm asking what is the probability. Okay. So what is the probability that S is contained inside V1? What is the probability of this? Okay. So this is same as saying probability, okay, V1 is in V1, V2 is in V1, and dot dot dot, and Vk is in V1. That's it. This is exactly equal to this, right? S is contained inside this, which means this is contained inside this, and that is or these are independent events, which implies this is equal to probability that Vi, it's a product over I going from 1 to k, okay, Vi is in S, sorry, Vi is in capital V1. What is this? What is the probability that Vi is in V1? Half. So this is equal to 1 over 2 power k, because half, 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 half product. Okay, excellent. Okay. Okay. But we wanted two things, right? So this is just, but what we are interested in, so let's write it down, right? So what are we interested in? Probability that S is contained inside V1 and W is contained inside V2. But this is independent event and this is also an independent event, because we can write this and whatever I wrote everything, right? So this is like, it is same as saying probability S is contained inside V1 time, and it is equality. So I am not using anything which is equal to one over 4 to the power k. So I designed a polynomial time algorithm whose success probability is how much? 1 over 4 to the power k, right? So we have designed a polynomial time algorithm whose success probability is 1 over 4 to the power k. And if I gave you this partition, you know how to find it, vertex cover. What? You will take V2, n of V2 is your vertex cover, done, right? So what does my algorithm does is that it constructs such a partition, okay, for every one. Now output S equal to n of V2. That's it. That's my algorithm. That's all that it does. Okay. But you might ask, no? Hey, but I made a polynomial time algorithm, no? Like, sounds something funky. Okay. So what did we achieve? Okay. We find a vertex cover of size at most k if exists in time poly n. And what is the success probability of this algorithm? But in randomized algorithm, we need to have a success probability which is constant. But 1 to the power 4 power k is not constant. So what can I do to make it constant? What should I do? Okay. So this is an algorithm. I make independent trials. Okay. I will run this algorithm. Let's call this algorithm A. Run A. Let's say 4 power k times. I run this much times. It's fine, right? If either run returns vertex cover of size at most k, return the same. Else, say no vertex cover, size at most k. Agreed? That's it. Now, what is the probability that algorithm will succeed? Right? Algorithm succeeds if it succeeds in either of the run. Right? We are running it so many times. If any of this, because that's what we do, right? If whenever you succeeded in finding a k size vertex cover, I said take it, because that is all that you asked me, no? I mean, I'm very happy. And this algorithm definitely runs in time 4 power k polynomial, because each run is poly time and I have repeated some 4 to the power k times. So the running time is perfectly fine. Okay. So now this looks like f of k poly in n, right? But what is the success? Have we boosted the success probability of this algorithm? Let's see. Okay. So what is the failure probability? Let's compute failure probability. So what is the probability that it failed in the first round? Is upper bounded by this? Because you succeeded with probability at least 1 over 4 power k, then you failed with probability at most 1 minus 1 by. And you failed in the first round and second round, and these are independent algorithms, right? So they are basically independently you have to boost their probability, because the set of random variables which is used in first run is not the same in the second run. We completely start from scratch. Okay? So this implies the failure probability of whole algorithm is this. But what is this number? This is like 1 over E. This is 1 over E. Right? So what is the success probability? At least, which is great, no? Which is great. Okay, so if you, let's run it. I boosted, right? So this is my success probability. So it's a randomized algorithm, right? But it's very simple, no? What idea was very simple. That look, I have a vertex cover. To witness that it is a vertex cover, all I care about is some k-size object which is disjoint from him, right? So I try to create a witness. W was a witness which was disjoint from my vertex cover, which is of small size. And whenever you have whenever for something I have a disjoint witness, I can say let's randomly divide them. One will go into because they are disjoint, so I don't have to collide, right? Everybody can go very nicely into one part, others can go into other part, and then we can play the game, right? And since the size of the structure which I want in one side is upper bounded by some function of k, size of the structure which we want in the other side is bounded by function of k. So then the success probability, because what are we doing? Independently doing some partition, right? So this is good, right? Because but then you have to prove this step. My problem, disjoint witness. Disjoint witness, even if it is like into some put into some small cave, I can still see my solution. If I can do some of these things, then that's a good way of designing an algorithm. So that's my first algorithm for vertex cover.
Is it a FPT algorithm?
Why it is not an FPT algorithm? It's an algorithm whose running time is this. It's just a randomized FPT algorithm. Because what did we say about FPT? Running time. Did we talk about randomness? Nothing. All I said, design me an algorithm whose running time you can bound as this. So when you say FPT, it absolutely makes no sense. It is FPT with respect to solution size, because it could be FPT with respect to solution size, but it may not be FPT by max degree. Okay. So it is a randomized FPT algorithm. That if you say, I will agree, but it is definitely an FPT algorithm. Okay. So it's a randomized FPT algorithm. That's it. That's all. This is fine. Of course, we should try to design a deterministic algorithm. We will do that. Don't worry. Okay, I still have 3-4 minutes. So, she said it's a good idea for vertex cover problem to pick a vertex of maximum degree. Can you give me an instance where this idea will not lead to an answer? You understand my point? So her heuristic was okay. So what's her heuristic or idea? Let's say, let us focus on a vertex of max degree, and in and around that. That's what so. But I'm just asking, could you come up with an instance where if I apply this idea, we never lead to an optimal algorithm? Right? So, or rather, could you come up with a counter example Give me a concrete example, Ananya. You can. So just think. Wheel graph. This. Yeah, it works. But I want where it doesn't work.
But there is a cycle also.
Oh, you want cycle also? This is not wheel. This is called star.
Wheel is
It's okay. It's okay. It's called star. Okay. Because it looks like a star, no? That's it.
If you take one more edges in on M.
Right? So okay. Okay. So let's make. No, we don't need this. Okay. Okay. Now, which vertex will you pick? It looks like picking this vertex is good, right? Because of our heuristics, right? Because that is definitely high degree. But if you pick this, you still have to pick how many vertex? 1, 2, 3, 4, right? Because who will take care of these edges? So this is like 5. But we could have taken just these 4 vertices, right? And that would have been heaven. Okay. Okay. So can I write a lemma and leave you as an exercise, and we'll take it up next week? Okay. But think. I mean, if you want to use Google or search and this, you're free to use. Hopefully, you will not find anything. Okay, so here is my. Let J be a graph, okay, and I'm going to sort. Like I'm just going to take her idea and say, is it just an? Yeah, we found some sort of counterexample, but I'm going to make it like slightly. I said, you maybe avoid one max degree vertex, but maybe may not be avoid second max degree vertex. Maybe if I find 2 first max degree vertex, you may not be able to avoid. Maybe 10, then you may not be avoid, right? Someone has to go and intersect with them. Okay. Okay. Let J be a graph and assume that G has a vertex cover of size at most k. As at most k. So it's basically an yes instance. Okay, this is my lemma. Okay. Let further say G is connected. So basically no isolated vertex. Otherwise those are, we don't know what to do with. So let's say no isolated vertex. I don't think, yeah, this can create. Okay. Now let V1, V2, Vn be an ordering of vertices such that, what is the property? Degree of V1 is greater than or equal to degree of V2 greater than or equal to degree of V1. So this is highest degree vertex, this is second highest degree, okay. Let Sk plus 1 be V1, V2, Vk plus 1, okay. So I want to say there exists a vertex cover of G of size at most k, say S, such that S intersection xk plus 1 is not equal to empty. You understand my point? So this is just a combinatorial statement. This I don't no algorithm. I'm saying to you, here's a graph which has a vertex cover of size at most k. So that's my assertion. Now I have given you a process. I said, look at the top k plus 1 vertices of highest degree, Sk plus 1. I'm saying there exists a vertex cover G of size at most k, say S, whose intersection with top k plus 1 vertices is non-empty. Okay. So I don't know first one is in the solution or the second one in the solution, but I can guarantee you that if you pick up the top k plus 1, one of them goes into a solution. Okay. If you find it difficult to prove with k plus 1, try to prove with any 10k, 20k, anything, and I will be happy. Okay? Okay. So I think that's all that I want to say for today, and that's a good place to take a break. Okay? Thanks, until unless you have a question, and I'm done.
Did you say we are guaranteeing that one of the
Yeah, that's what there exist. No, proof there exists a vertex cover G of size at most k, say S, such that this happens. I mean,
there can exist another vertex cover such that intersection.
this statement says nothing about that. This statement says it could be, but maybe for proof you can replace by there exists to for all, but that you check for your proof. Because when I ask you for all, I am asking you much stronger statement to prove, but when I say there exist, I am asking you a weaker statement to prove. So I am guaranteeing, right? There exists a vertex cover where I am guaranteeing that it contains a vertex cover, one element from top k plus 1 vertices. This is what, by guarantee meaning this only guarantee. I cannot guarantee for everything.
The information about the degree is highest degree.
Huh? Yeah, I wrote, no? What is sk plus 1 is v1 to vk plus 1. These are the top k plus 1 vertices of the highest degree. Because look at this, they are ordered in degree of v1 is greater than or equal to degree of v2 and so on and so forth, right? What's your, are you still doubt? Fine. Okay. So if there is no further question, then let's